Hello everybody. Today we're going to talk about real numbers. So you might be asking yourself what a real number is. Well, not every number, believe it or not, is a real number. We also have things in Algebra 2, such as imaginary numbers. So we have imaginary. We also have complex, which is a combination of a real number and an imaginary number. But again, not every number is a real number. So real numbers are numbers that you use in everyday life. So if you think of everyday life, we have positive numbers, we have negative numbers, we have fractions, we have terminating decimals, like you're buying something at the store. We have repeating decimals, even something like 4.5858 repeating. So even zero. So real numbers could be a lot of different things. Pi, okay, a circle circumference divided by its area. All these different things are real numbers. So real numbers that we use in everyday life. And also, we can graph them on a number line. That's very important. So we can graph real numbers on a number line. So if you remember a number line from previous courses, usually you have 0 in the middle, and you have your positive numbers to the right and your negative numbers to the left. So usually, when you're explaining to somebody how to graph a real number, you usually say to move right or left from 0. With that being said, not every single number line has to have 0 in the middle, but most often they do. Okay? So now let's graph a real number. So let's make a quick number line. And apologize for my number line not being perfectly straight, but it's nice to have this active narration of the program. So when you're using your line paper, it'll be a lot easier to make your number lines. So let's say we have -3. That's a really easy number to graph. So we go from 0 and we go left 3 places. So we put a dot there at -3. So that's how we would graph -3. Now let's try another one that's maybe not as easy. Let's say we have 11/3. Now, we're doing this without a calculator. So a couple things I want you guys to notice. First of all, that the numerator is larger than the denominator. So what that tells us is this fraction is greater than 1. So before we even do anything, we know this fraction is greater than 1. A lot of students would say this is an improper fraction. We don't really use that term in algebra, although it is true that it's improper if the numerator is larger than the denominator. But you'll find that in algebra and a lot of high-level mathematics, you often have these improper fractions. So you really don't use that term too much anymore because these are guaranteed to be exact answers. So let's graph this. Now, what we need to graph this is we need to know where 11/3 lies. So what we're going to do is we're going to convert this to a decimal. So how do you do that? Well, you always divide the numerator by the denominator, and that's always, okay? So the numerator always goes underneath your division sign. Your denominator always goes on the outside, being your divisor, okay? Let me go to a new slide to graph this. It would be between 3 and 4. And since it's 3.7, it's going to be very tough to do in here, but you should make probably 9 marks on between the two integers here. So 3 and 4. And because it was about 3.7, I'm going to put it on the 7th mark. Okay? I made it a lot bigger so you could see it, but that's how you be really accurate. And the way we did it here, each mark is a 1/10 of a unit. So you make 9 marks, your 10th mark would be your next integer value. But again, for a fraction, you always divide the numerator by the denominator. And now if you're graphing it, you could round to the nearest 10th. So we have, to rewrite that problem again, I'm going to put 0.00 on the end of 11 in case we need to keep going. Now, right away, you can bring up your decimal point. So 3 does not go into 1, but it does go into 11, and it goes in 3 times. So we want to know how many times it goes in without going over. So we want the maximum amount of times it goes in without going over. Now we multiply these two and get 9. Now you subtract and get 2. We bring down the next 0. By the way, we know this answer is correct so far because 2 is less than 3. So 3 goes into 20 6 times. 6 times 3 is 18. And we subtract, we get 2, and we bring down a 0 again. Now, normally I would write out this process, but if you look, it's exactly the same answer as before, so we know 6 is going to go in there. So this is going to be 6, 6 repeating. So if we round this to the nearest tenth, it's going to be about 3.7. So if we go back to help you graph it. So go ahead and try and graph this one really quick here. Go ahead and graph, let's do negative 23 over 8. Go ahead and graph that on your number line. Okay, so what I want you to do right now is pause the video, graph this properly, and then after you're done, restart the video, see if you got the answer correct. So stop the video right now. Okay, so here's the work shown. When you divide this out, you're going to again divide your numerator by your denominator. It doesn't matter the size of each numerator and denominator. So the 23 went underneath our division sign, called our dividend, and the 8 went on the outside, called our divisor. When we divide this out, we get 2.875. So we could round that up to about 2.9 if we're rounding to the nearest tenth. Now, we've got to make that final answer negative. Some students do all that work, and they do a great job, and then they forget to make it negative at the end. So to graph this, we're going to make 9 marks in between and put it on that 9th mark, going to the left because it's negative. Now, if you have you don't necessarily, that you know where it lies, you don't necessarily have to convert it to a decimal. So what I mean by that is, sometimes you get an easy fraction like 3/5. Now, if you look at this fraction, you should know it is less than 1 because the numerator is smaller than the denominator. But for this particular problem, what I can do is, since it's less than 1, it's positive though, I can make 4 marks in between because the denominator is 5. So that's making this fraction into 5 pieces and put it on the 3rd mark. So if it's a nice fraction that has a smaller denominator, you could do something like that. If not, convert this to a decimal. So we would divide 3, our numerator, so make it 3.00, by 5. And when you divide this out, you're actually going to get 0.6, which would give you the exact same answer. Okay, so now let's graph 3 numbers on a number line. So let's graph negative 2, 1/4, and negative 17 over 9. So if we graph these in the same number line, first we'll start with negative 2. Get the easy one out of the way. So we go left 2 units and put a point. Next we'll do another easy one, 1/4. That's between 0 and 1. And if you convert that to a decimal, it's about 0.25. So if you divide the numerator by the denominator, or you could break this into 4 equal parts and put it on the 1st mark. And the last one is negative 17 over 9. This one we're going to write out. So we have 17 divided by 9. So 17.00. 9 does not go into 1, but it does go into 17 one time. Remainder 8. 9 goes into 80. Bring up my decimal point here. Probably should have done that before. 9 goes into 88 times. Remainder of 8. And 9 goes into 80. Another additional 8 times. So it looks like it's going to be 0.8 repeating. So remember to make it negative. So if we want, we could round that to a negative 1.9. So it'd be very, very close to that negative 2. Going to the left. Now, look at that number line very carefully. A couple definitions I want to talk about really quick. If we were to list these numbers in increasing order, we would say, and this is increasing order now. Let me just use a different pen to highlight this a little better. We would have negative 2. Well, that's the same pen. There we go. We'd have negative 2, and then a negative 17 over 9. And then 1/4. That would be an increasing order going from left to right on the number line, from smaller numbers to larger numbers. So this here would be increasing order. If we were doing decreasing order, all we'd have to do would be reverse that. So for decreasing order, we actually go from the right to the left on our number line. Okay? So that's how you do increasing and decreasing order, especially if you have a lot of values where they're difficult decimals. For increasing order, go left to right on your number line. For decreasing order, go right to left on your number line. Increasing order. So increasing order would be from the largest number, or excuse me, let me rephrase that, would be from the smallest number to the largest number. So that's would be increasing order. So decreasing is the reverse. Decreasing is from the largest number to the smallest. And notice I kind of did the way I did that because that's the way it's going to go on a number line. So if we go back to, so a couple more other things we want to talk about really quick. So I'm going to write down some numbers, and they're going to appear right away. So these numbers, the left of the two sets of columns that we made, numbers that are in the box, those are called perfect squares. So perfect squares are numbers that when we take the square root of them, which would be the symbol right here, the answer is an integer. So for example, the square root of 36 equals 6. Okay, and square root, again, we're asking ourselves, what number times itself gives us the number underneath the square root, or the radicand? So the square root of 36, that would be 6, because 6 times 6 is 36. Look at our perfect squares. 27 is not on here, but 27 is between 25 and 36. Well, the square root of 25 is 5, and the square root of 36 is 6. So since we're taking the square root of 26, so look at these perfect squares again, the numbers in boxes. It has to be between 5 and 6. Now, if you remember, we had our perfect squares, and 27 is between those two perfect squares. It's definitely a lot closer to 25 than it is to 36. So therefore, we'd probably estimate this to be about 5.2, maybe 5.3. So if you said about 5.2 or 5.3, you're definitely pretty accurate there. So again, you're going to use your perfect squares to help you estimate square roots. So let's say we're comparing 3 over 5 and 0.66. Well, we want to put these numbers in equivalent forms, or the same form. So right now, one's a fraction and one's a decimal. So in order to compare these most effectively, we want to make them both either fractions or decimals. In this case, it's probably going to be easiest to make 3 over 5 into a decimal. So if you divide 3 by 5, like we talked about before, you're going to get an answer of, and this is very quick, 0.6. So with getting that answer, that would be 0.60 if you want to add another place, so you just have the same place values. But you should be able now to clearly see that 0.66 is a larger number. Now be careful if the numbers are negative, because if these numbers were both negative, the opposite would be true, because the closer a number is to 0, if it's negative, the greater it is. So just be careful with your negative values. But in this case, by making them both decimals, it's easy to see which number is greater. So let's talk about one more comparing. Let's say we have 3 over 8, and we're comparing that to, we'll do 5 over 16. Well, these are two fractions. They're both in the same form, but the problem here is the denominators are different. So that means each of these fractions are not in proportional sizes. So what we want to do is we want to make these denominators the same by getting common denominators. So the least common denominator, or least common multiple between 8 and 16, is 16. So what we're going to do is we're going to times the numerator and denominator of this one by 2. And now we get 6 over 16. And now that these fractions have the same denominator, the pieces we're breaking into are the same size. So now it's easy to see that 3 over 8 was actually greater than 5 over 16. So hopefully this video lesson was helpful. If you have any questions, please let me know. Thank you for your attention, and have a fantastic day.